Good evening to Dr. Rosetta and Dr. Dean. My name is Sumiti Ilamaran. My metric number is 196508. Okay, the given title for us is production of ethylene 500 ton per month by using naphtha as raw material. Okay, our company's aim is to produce ethylene with purity 99.9%. The raw material which we are using to produce ethylene is naphtha to produce 500 ton per ethylene per month. Okay, this is our plant process flow diagram, which we started with pump, heater, and then furnace, quench tower, compressor, cooler, continuous absorber, boiler, dehydrogenator, demethanizer, deethanizer, and then compressor, C2 splitter, and split condenser. Okay, this is my very first unit, which is pump. Okay, the function of pump. In every plant, raw material input should be in standard condition, which is 1 atm pressure and 25 degrees Celsius. Pump is used to pressurize the standard condition naphtha, fat naphtha, before it charged into heater. Okay, the inlet temperature of pump is 20 degrees Celsius and 1 atm bar, with flow rate of 244 kmol per hour of naphtha. My outlet temperature is 20 degrees Celsius, but the pressure has been increased to 2.69 bar. Okay, I've been used mechanical energy balance to calculate my work shaft and heat produced in this unit. My reference point is 20 degrees Celsius and 1 atm. The work shaft which calculated from energy balance is negative 1.1257526.39 kilojoule per second, and my heat is positive 1257526.4 kilowatt. Okay, and then followed by heat exchanger. Heat exchanger I use to preheat the heavy naphtha before it charged into furnace for further cracking. My inlet temperature in heat exchanger is 20 degrees Celsius and my inlet pressure is 2.69 bar. My outlet temperature is 616 degrees Celsius and 5.8 atm. Okay, my reference point at this unit is 20 degrees Celsius and 1.01325 bar. Heat produced in this unit is 8.98 times 10 to the power of 7 kilojoule per mole. Next, the heavy naphtha which is preheated in heater is charged into furnace for further thermal cracking in order to crack the heavy naphtha into smaller hydrocarbon. Okay, the hydrocarbon which is discharged from heater is diluted with water, 465.855 kmol per hour of steam to produce this amount of smaller hydrocarbon. Okay, my reference point at this unit is 25 degrees Celsius and 1 atm. The heat produced in furnace is 1.24 10 times 10 to the power of 1.24 10 to the power of 4 kilowatts.
Okay, hello, my name is Muhammad Al-Alif Irfan. My matrix number is 199090. So next I am going to explain about quench tower. Quench tower is the next unit after furnace. After furnace, the temperature is 865 degrees. Quench tower need to cool down the stream from 865 to 345 to 349 Celsius. This is because if we want to enter the compressor, we need to lower down the temperature so that the compressor will not be damaged so much. The quench tower Energy balance calculation, I use the usual theoretical method to find and I use the inlet as the reference and to find the head of enthalpy in the outlet. So after I multiply the molar flow rate and the head of enthalpy in the outlet, I managed to get the negative Q value. The negative Q value is given because the temperature is decreasing. So after cool down the stream, then you enter the compressor. The compressor compress all the products from 2.20 atm until 35 atm. When we compress the product, the pressure will increase. Also, the temperature will also increase. This this compressor is a multiple bed compressor, and the actual purposes is to compress the light products that have the lower carbon numbers for it to be easier to be removed. Then next, after we compress, because the temperature is very high until it reach at hundreds, we need to cool it down until it reach 100 degrees, because uh, in the next stage you need to absorb the water. So for the energy balance calculation for the compressor, I use the same theoretical pathway and use inlet as the reference. Also, the pressure does not affect very much because it is compressed in the vapor state. Next, in the cooler, I also use the usual theoretical pathway using inlet as the reference state, and I managed to get negative Q value because the temperature is decreasing, so the heat is released from the system, and the Q value is very high because some of the products experience phase change, such as butane, pentane, hexane, and water, because 100 degrees is past their boiling point. Next, after I cool down the products, we enter the adsorber. The adsorber is aimed to remove the water from the stream. We use disolate 3A as the molecular sieve to remove the water. So for the energy balance calculation, I use the usual theoretical pathway and get the negative Q value because of the decreasing in temperature in the water outlet. So the water that is in the liquid form will be absorbed by the molecular sieve. So after the water and CO being completely absorbed, the remaining products will go to the next stream.
I'm Sudhakar Doctor. My name is Lu Junli and my metric number is 1999181. Today I'm going to present about boiler, dehydrogenator, remethanizer, and dethanizer. For boiler, the inlet temperature is 100 degrees Celsius while the outlet temperature is 140 degrees Celsius. The inlet pressure and outlet pressure are the same, which is 38 bar. The molar flow rate and the mole fraction of all hydrocarbon compounds in the inlet stream are the same as the outlet stream. And for energy balance, there is no phase change from inlet to outlet stream, and all the hydrocarbon compounds are mixed as gas in inlet and outlet streams. So we can calculate the total Q by using the balance on non-reactive reaction and hypothetical pathway. The total Q is 1.24 E plus 03. Next, we move on to the hydrogenator. The inlet pressure of the hydrogenator is 140 degrees Celsius, but the overhead outlet stream is negative 19 degrees Celsius, while the bottom stream is 45 degrees Celsius. The inlet pressure is 38 bar, while the overhead stream is 23 bar, and the bottom stream is 31.4 bar. Same as the boiler, we can use the hypothetical pathway and the balance on non-reactive reaction to calculate the energy balance and get the total Q, which is negative 2300 ECH3115 kilojoule per second. Next, we move on to the demethanizer. The inlet pressure of demethanizer is negative 45 degrees Celsius. The overhead outlet stream temperature is negative 17.1 degrees Celsius. The bottom one is 5 degrees Celsius. The inlet pressure of the methanizer is 31.4 bar and the overhead outlet stream is 5.4 bar and the bottom one is 26 bar. And we can use the balance on non-reactive reaction and hypothetical pathway to calculate the energy balance, which is total Q, and we get the total Q, which is negative 2530.83752 kilojoule per second. Next, we move on to the ethanizer. The inlet pressure of the ethanizer is 5 degrees Celsius, while the overhead outlet stream temperature is negative 15.8 degrees Celsius, while the bottom one is 70 degrees Celsius. The inlet pressure of the ethanizer is 26 bar and the overhead outlet stream is 1 bar, while the bottom one is 15 bar. And we can calculate the energy balance by using the balance on non-reactive reactions and hypothetical pathway, and we can get the Q, which is negative 1855.211204 kilojoule per second. Thank you.
Assalamu alaikum. My name is Sumaya Hassan and my metric number is 191350. And today I'm going to explain about the three last units of our ethylene production. The inlet stream of the compressor coming from the de-ethanizer, the unit before, at a temperature of 180 m. So the compressor's function is to increase the pressure from 180 m in the inlet to 9.789318 atmospheric pressure to the inlet. After that, we can calculate the enthalpy changes associated with the pressure changed and the slight increase of the temperature in the outlet, and then we're gonna calculate the heat transfer, and it turned out the heat transfer is negative 18.5.211204 kilojoule per second. Going to the next unit is a separation unit to get our product as pure as possible, and it's a C2 splitter, and the stream goes as a gaseous state. It goes in a negative 16.8 Celsius temperature and 9.78 bar, and it will be separated into two products, the upper stream and the bottom stream. The upper stream is vapor status and the bottom stream is a liquid status, and they will both have the same temperature and pressure. After that, we're gonna calculate the enthalpy change associated with the pressure, temperature, and the phase change, and then the Q. And it turned out the Q outlet is 26.63645074 kilojoule per second. After that, our last unit is the condenser, which the function is to take the vapor product that we want and convert it to a liquid, and it goes the inlet in the temperature of negative 31 Celsius and 19 bar, and it comes out as in 19 bar, so the pressure will remain the same and temperature will slightly decrease to negative 120. After that, we will calculate the Q associated with that, and we turn out that the Q is negative 5394 to the power of negative 5 kilojoule per Celsius. This is all from me. Thank you so much.
Okay, so the last one is the costing. The costing, I am going to include the price of naphtha and the price of ethylene. This is the price of naphtha. This is the highest in the 10 years time, and this is the lowest in the 10 years time. This is also the highest price of ethylene in the 10 years time, and the lowest price of ethylene in the 10 years time. This is the maximum price for a month value of naphtha use, and this is the minimum price. This is the maximum price of ethylene produced in a month, and this is the minimum price of ethylene produced in a month also. So this is the minimum selling price and the minimum and the maximum selling price. So the profit of the minimum selling price is very negative. It is very high loss. Now it is a very quite not very big loss, because the selling price is, we use the highest price of ethylene, and the costing price we use the lowest price of naphtha. But for the maximum price, we almost lost about 9 million because of the selling price. We use the highest price of naphtha, and the costing we use, and the selling we use this lowest price of ethylene, and the costing price we use the highest price of the naphtha. So this is the raw materials that we use in the plant. The naphtha, the feed, the zeolite is used in the adsorber. We use almost 100,000 200,000 ton per year, and the coal used in the boiler about 47 ton per year, and water we use in the furnace, but we use in the liquid phase, so we need to convert to the steam. This is the price per meter cube, and this is the unit operation price. As you guys can see here, the highest one is the distillation column, because it includes the hydrogenator, the methanizer, and the ethanizer, also the C2 splitter. It is all in the distillation column. So the total cost of the unit does not reach 1 million. So for the operating cost, we use the a little bit of the from this price. We use a little bit, and for the actual raw materials, we use from this one. Sorry, the actual material is from this one, and the operating cost is from the tax. So if you add, this is the actual value that we use per year for the production of ethylene, and the conclusion is around 99.81 purity of ethylene is produced. It does not reach our main, because we need 99.99. So around 500 ton of ethylene per month is produced by using 1,000 ton of naphtha per month. This is the revenue. So the recommendation is the conversion of naphtha to ethylene must be higher. This is to increase our profit, because right now our conversion yield is very low. So we need to increase the conversion yield by using the perfect temperature and the perfect pressure. So we can also sell the unwanted product. There is a lot of unwanted products such as hexane, butane, methane, and ethane. We can sell those products to increase our profit. Then we need to recycle the water used in the furnace, because the water is being removed at the adsorber. So the removed water can be recycled back in the furnace to use to assist the steam cracking. And also we need to use the same unit to heat the alcohol mixture. In our plant we have heater, boiler. So for the recommendation, I think we need to use either boiler or heater, and then we recycle the unit back. Okay, that's all. Thank you.